And so theorem 4.72, that's what we just derived. So A, an M times N matrix, B must be in Rm, M components, and X0 a fixed, or sometimes the book says it's special. So essentially that is any solutions you pick, and because you pick, it's special. No? A special solution of A times X equal to B. And furthermore, V1 to Vk, a basis of the null space of A. That means, again, the dimension of the null space is K, because we have a basis with K elements. Then we have the following result. Y is a solution of A times X equal to B. So that's actually what people are looking for. If and only if. That's what we just proved. Y is equal to X0, my fixed solution, plus a linear combination of the bases. So this here is in the null space of A. That means every solution can be always written as one fixed solution, and this one you pick once and forever. No? Also, there are many for them, but once you pick one that's fixed, plus an element of the null space, or also sometimes called the kernel of A. So this is how every solution of AX equal to B looks like if you have a solution. No? Also, maybe there's no solution, but that's we will address in the next section. Yeah? So the point is, solutions always have this special shape. And it turns out, now you say, okay, so what about this? How do I get this? It turns out we already got this all the time. This comes directly out of the Gauss-Jordan algorithm. And so I like to stop now for a break. So after the break, we do one more time an example where we see this relationship, and we see, in order to get it, how do I get V1, V2, Vk, and how do I actually know K anyway? All this is already in the Gauss algorithm. The Gauss algorithm tells you everything. The only thing which is different now than section 1 is now we read it in this way that we say, oh, this result of the Gauss algorithm means actually the null space has this dimension, no? For example, no? Or these vectors are a basis of the null space, and so on. So nothing changes in the calculation, but we know better what the results of the calculation actually means. It's not just a set of parameters. There's actually more. Okay, so like I said, after the break, I would like to do an example. It's a little bit larger, but if you make the example too small, you don't see actually all the things. So it's good to have a larger example, so we see really how all these things play together. Okay, and then maybe after the break, I already start with section 4.8 also later, but I'm not sure if I can finish 4.8, but we still have time tomorrow to finish then chapter 4. So if there are no more questions, I would stop for like a 10 minutes break again. Any more questions about this in the moment?
No questions from me, thank you.
Okay, so then I just stop sharing. And we have 10 minutes break, so by around 10:15, I continue then. Thank you. And then I share my screen again. And we continue where we left off. So this was the result which I wrote down before the break. So we have a solution of this equation system is always given by a fixed solution or a special solution plus elements of the null space. Okay, so, and we like to see this formula now in a concrete example with numbers. So, and as I said, we need a little bit larger example. So I only write down here the linear equation system, and then I go to next page where we actually do the reduced row echelon form. So our linear equation system looks the following. So we have 1, 3, -2, 0, 2, 0. Then we have 2, 6, -5, -2, 4, -3, 0, 0, 5, 10, 0, 15. And then we have 2, 6, 0, 8, 4, and 18. Times, now comes our vector of unknowns or variables. We have 1, 2, 3, 4, 5, 6 columns, so we need 6 variables. Equal to, and then we need a right-hand side with 4 numbers, which is here 0, -1, 5, and 6. So this is our linear equation system. So this is our matrix A. In this case, it's 4 by 6. This is our vector of unknowns x, and this is our right-hand side B. So A times x equal to B, as usual, A, x, and B. Okay, and the question would be again, find all solutions. We have done this since chapter 1, but now with this result, we write down the interpretation as every solution is given by a fixed vector or special vector x0 plus an element of the null space. Okay, so in order to do reduced row echelon form, I start a new page. So this is my, so I write down the augmented matrix. So we do reduced row echelon form. So 1, 3, -2, 0, 2, 0. Right-hand side 0. Then we have 2, 6, -5, -2, 4, -3, -1, 0, 0, 5, 10, 0, 15, and 5. And then we have 2, 6, 0, 8, 4, 18, and the right-hand side was 6. Okay, maybe I should better check one more time. 2, 6, 0, 8, 4, 18, 6, 0, 0, 4, 10, 0, 15, 5, 2, 6, -5, -4, -3, -1, 1, 3, -2, 0, 2, 0, 2. Okay. Okay, so this is what we like to solve. And we go as usual. The one here is already perfect. The books makes it actually easy for us. So we make -2 times row 1 and -2 times row 1 to generate zeros here and zeros here. First row doesn't change. 1, 3, -2, 0, 2, 0, 0. Then this -2 times this is 0. This -2 times this is 0. This -2 times this is -1. This -2 times this is -2. This -2 times this is 0. This -2 times this is -3, -1. Third row has not been changed. And then this -2 times this is 0. This -2 times this is 0. Sorry. This -2 times this is 4. This -2 times this is 8. This -2 times this is 0. This -2 times this is 18. This -2 times this is 6. Again, we see, oh, there's a -1 that's nearly perfect. So we can turn this in easily into 1 by multiplying this equation by -1. Then I have a 1. but just to save a little bit writing, at the same time, I make a 0 here and a 0 here. So we add 5 times row 2, and we add 4 times row 2. Now we get, first row doesn't change, 1, 3, minus 2, 0, 2, 0, 0. This times negative 1. This plus 5 times this. Okay, that becomes totally 0. And then this plus 4 times this. 6, 0. Oh, sorry. 6 plus 4 is 2. Okay, so first this is a 0 row. So we have to put it on the bottom. And at the same time, 6, 2, I turn this into leading 1 by also dividing by 6. So you see that's actually not so bad, even it looks big. 1, 3, minus 2, 0, 2, 0, 0, 0, 0, 1, 2, 0, 3, 1, 0, 0, 0, 0, 0, 1, 1/3. The 2 6 is 1/3. And we have a 0 row. Okay, and so now we have row echelon form with 3 leading ones. Now we bring it to reduced row echelon form by eliminating the non-zero numbers on top of the leading ones. Again, we start now from right to left. So here we eliminate this here. So, okay, sorry, I just looked at my notes. Minus 3 times row 3. And so now only this one changes. So we get 1, 3, negative 1, 0, 2, 0, 0. Then we have 0, 0, 1, 2, 0, 0. This minus 3 times this gives me a 0 here. Then we have 0, 0, 0, 0, 0, 1, 0. And a row of zeros will not affect our solution. And finally, we have to eliminate this, plus 2 times row 2 to get rid of this guy. And I forgot the 1/3, sorry. So this plus 2 times this is 1, 3, 0, 4, 2, 0, 0. Then we have 0, 0, 1, 2, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1/3, 0, 0, 0, 0, 0, 0, 0. Okay, and we see 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. So these are our leading ones, and everything else in this column is 0. So we are at reduced row echelon form. So we can just read off our solution. And now, for the first time, I will do something which I always say I can do, but I've never done until now. But now I just like to show you that in this example, what I always mean by this. So let's say this is x1, this is x2, this is x3, this is x4, this is x5, and this is x6. Now, I reorder my variables. Keep in mind, the variables are names anyway. I call them x1, 2, 3, 4. Someone else might call them v, w, x, y, z, and whatever the next letter would be. So I reorder now my variables. Like I said, they are just names anyway. Sorry, should have a little more space. So let's say starting from here. So what I do is I make x1, x3, x6 first. So these are the variables for the leading ones, and then all the rest, x2, x4, x5. and the right-hand side. So all what I've done is I renumber my variables. So then we have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. And then comes for x2, it's 3, 0, 0, 0. For x4, it's 4, 2, 0, 0. And for x5, it's 2, 0, 0, 0. And then we have again, this has not changed, 1/3, 0. And now you see what I always do. I say, okay, we can always assume after column change that here on top we have identity matrix. Then we have a block where everything can happen. So that can be full of non-zero numbers. In our case, we are lucky, there are a lot of zeros, but that can be really a full matrix. And then on the bottom, we always have a block of only zeros. No? And it's consistent if this guy here is 0. But this guy is 0, so we know it's consistent. Okay, so this is, so you see always now what I mean by assuming that the columns are correctly ordered, we can always assume that in the reduced row echelon form at the beginning, there's an identity matrix. Okay, so now, but otherwise this is like what we always do since chapter 1. So we have the leading 1 variables. We have x1, x3, and x6. And then we have 2, 4, and 5. These are the variables which get a parameter. Sometimes we also call them free variables or parameters. These are x2, x4, and x5. And also, obviously, a variable is either a leading 1 variable or a parameter or free variable. It's either this or this. So the sum of the 2 types of variables is always equal to the sum of the columns. So in general, number of leading 1 variables plus number of parameters. When you add them, it's always n. No? In our case, n is equal to 6 because we have 6 columns. So this is again an equation which comes up with different names in the next section. So number of leading ones plus number of parameters is always equal to your n. Okay, so we have this equation. And now we do our usual thing. We split it, we put in parameters. So parameters go to x2, 4, and 5. So let's say x2 is equal to s, x4 is equal to t, and x5 is equal to u, where s, t, and u are arbitrary real numbers. Then we look for our leading 1 variables. So let's start with x6. So that means x6 is equal to, okay, 0, 0, 0. It doesn't mean anything. It just x6 is 1/3. Then the next one, x3. So I go backwards. x3 is 0. Okay, I don't write the 0. And then there's a 2x4. I bring it to the other side. It's minus 2x4, and this was t. So it's minus t. And then finally, we have x1. x1 here is, again, 0. I don't write it. Minus 3x2, so minus 3s. Then minus 4x4. x4 is t, minus 4t. And then minus 2x5. On the other side, x5 was u, minus 2u. So this is what we get. S, T, U are arbitrary numbers. X1, 3, and 6 are given by this. Okay, I need to go to another.
Professor?
Excuse me, Professor?
Would it be
why would
-2?
x3, yeah, that was my question. Why would x3 be -t? Wouldn't it be -2t?
Oh, yep, right. Thank you.
Thank you.
Anything else?
No, I was just confused about
Okay,
that.
no, that I just missed it from here. No,
Yeah, no
sorry.
problem.
Thank you. Okay, so now we copy this over as an equation for x1 through x6 to connect this finally to the result, which we had before the break. So now I copy this over. So we get x1, 2, 3, 4, 5, and 6 is equal to minus 3s minus 4t minus 2u s negative 2t t 5 is u and 6 is 1/3. Okay, now we see there s, t's, and u's. So I split this vector up now in constants, s, t's, and u's. So there's only one constant here. All the others have a 0. 1, 2, 3, 4, 5, 1/3. Plus everything with s, minus 3s, s, and no more s, plus everything with t, minus 4t, 0, minus 2t, t, 0, 0, plus everything with u, minus 2u, no u, no u, no u, 1u, 1/3. Okay, now SS, TTT, UU, we factor, no, sorry, and no 1/3. Okay, and so now we finally get 0, 0, 0, 0, 0, 1/3 plus S times minus 3, 1, 0, 0, 0, 0 plus T times minus 4, 0, minus 2, 1, 0, 0 plus U times minus 2, 0, 0, 0, 1, 0. And again, STU can be any real number. So maybe I should write this one more time here. So it turns out this here is the span of these three vectors. So span. And it turns out that's actually the null space of A. And this is X0. That's a special solution. So this is where this now fits together with the final result of the previous slide. So Y is a solution. If and only if Y is a fixed solution, we pick this one. But you can have other ones. This is just one fixed solution which came out of the Gauss-Jordan, but there are infinitely many others. This is one possibility, plus something in the null space, and that's this. So this gives us the null space. This gives us one fixed solution. And now the last thing left is to write down the null space one more time. So not null space, sorry. Null space of A is the span of these three vectors, minus 3, 1, 0, 0, 0, 0. Then we have minus 4, 0, negative 2, 1, 0, 0. And minus 2, 0, 0, 0, 1, 0. So these three vectors generate the null space of A. Also keep this in mind what this means. If you take this vector, multiply by the matrix A, you get 0. It will not change anything. So that's why we can pick here any number in front. It doesn't matter because the matrix A will turn each of these vectors into a 0 vector. No? These are solutions to the homogeneous system. And now the final thing, which I said already yesterday, now we look here only in the rows where there is this 1, 1. No? Where, remember at the beginning, we always say x2 is S, x4 is T, x5 is U. So that means in row 2 is a 1, in row 4 is a 1, in row 5 is a 1 for the corresponding column. So now the columns were, rows were 2, 4, and 5. So 2, 4, sorry, 2, sorry, I'm already getting confused here, 4, and 5. So if you only look in row 2, 4, and 5, what we see is an identity matrix. So that means these vectors, forget about all the other components. If you just take these three components in rows 2, 4, and 5, then these red vectors are automatically linear independent. And then adding some stuff on top or bottom doesn't make a difference. So it turns out the vectors which come out of the Gauss algorithm are automatically linear independent. So it turns out not only that these three vectors span the null space, they are also automatically linear independent, which means this is a basis of the null space. And again, how did we do this? Yeah, because that's how we make it. We give a parameter to the different rows. That means in the end, you will always get in your long vectors for these rows, there's always an identity matrix which makes it automatically linear independent. So again, there's nothing to do. You just have to remember the formulas from the beginning. So whoever created the Gauss-Jordan algorithm, not necessarily Gauss and Jordan, usually the people who get the name, not necessarily the inventors, but it means this is very smart. No? So this means this is a basis of the null space, which also means the dimension of the null space of A for this matrix A, because we have a basis of 3 elements, is 3. So all this is without any extra calculation. You just do reduced row echelon form like we did since the beginning of the class. You give parameters to each column, which is not a leading one. You solve for the leading ones, and then automatically you get also a basis of the null space, you get automatically the dimension of the null space, and you get automatically one special solution. This is all already there since chapter 1. We just didn't have the language to talk about because we just introduced dimension yesterday, I think. Yeah. So, but now we know what we could get here is always a basis guaranteed, and the number of basis vectors is always equal to the dimension of the null space. And then the remaining part is always one fixed special solution. So that's also what I meant at the beginning of these 2 sections. Although there's another section coming, very similar in spirit to what we just did here. The point is, you will not learn a new calculation. All you learn in this section, which is now already finished, and the next section is whatever we did before, then suddenly we say, oh, that means this and this. So essentially, it's a new interpretation or a new insight based on the reduced row echelon form. Yeah. So in some sense, I hope that's actually good for you. It means there's nothing new to learn how to calculate things. It's just, oh, it means this and this now. No? Okay. I hope that was not too confusing now. And it turns out we will do very similar calculation right away at the beginning of the next section again. Okay, everything kind of clear here now for linear equation system. And again, also what you see here each time, nothing is square here. No, this is a 4×6 system. No, so this, whatever we say now, is for general linear equation systems. Oh, are we good?
Yes, thank you.
Okay, so then we go finally to the last section on linear equation system, which is 4.8. And 4.8 actually starts with the calculations very similar to this, but it leads us into another way of thinking about these row and column spaces. And it turns out also this 3 here will show up one more time. Again, it has some, we know already it's the dimension of the null space, but again, it has a relationship with the other things. Sorry, I always seem to miss the page which I'm looking for. Where was actually the solution of my system? Okay. Yeah. So it will again go back to this. And based on this, we now go in the next section in another direction and say, okay, let's say the number of leading ones, we always call it R. And so what else can we actually do with this representation? What does it actually mean for our original matrix A? And as I said, this is the last missing piece for linear equation systems in general. We take another example and we again go to the reduced row echelon form and start thinking one more time, what can we squeeze out as information out of this? Okay, and that is the start of section 4.8. Like I said, it's really now gets more computational. Okay, so if there are no more questions, then I stop the screen sharing and I finish the meeting. So, and again, 3 o'clock, if you like, we have office hours. And otherwise, I will see you tomorrow.